Right. So this is the smart card and the track. The smart card is attached to the end by a spring. So right now it is at equilibrium position. You can see it's not moving. That's considered position 0. And so right now the spring force is balanced by this component of gravity down the slope. So it's at rest. And if I pull the card, I can initiate an oscillating motion like this. Back and forth, back and forth. And then the graph of this motion, position time graph, velocity time graph, will all be a wave. Okay, let's see that. So let me pull out my app on the screen first, the SparkView app. All right, so SparkView, I'm going to start a new experiment. All right, so let me make sure the card is connected. Oh, it's not, so I need to turn on the gallery. Okay, now it's connected. Cancel. All right. So I'm going to change the period to 20 Hertz. All right. So I'm going to start the oscillating motion while at the same time start the app to record all the data and the graph. All right, so you can see this is a position time graph in real time. All right. So let's take a closer look at, and you can already see this is a wave. So let's take a closer look at this data. It has a lot of interesting stuff to talk about. There's a lot of fascinating features. So this is the PT graph. You can see it's a wave, and the VT graph, it's also a wave. So I'm gonna do a bit analysis on the graph. And again, I'm gonna use a previous trial I did because I already finished analyzing the data. It'll save us more time. So it's basically the same lab, just another trial. Here is motion. All right, so you can see it's the same pattern. All right, so a few things I want to talk about. First of all, you can read the amplitude from the graph. Like this middle line is the equilibrium, and this highest point is going to be the amplitude. So click on that, and 5.05, and it's at 0.111 meters. So the amplitude is 0.111 meters. And of course, the amplitude will decrease over time since there is a friction air resistance. Energy will be lost to heat. And that's why you see the amplitude decreasing. That's no surprising. But it's still a periodic motion. It's a still oscillating motion. And the period can be calculated by taking the time difference between the two crests, right? So we already have one crest here. And then let's do the other crest. And let's make sure this is the highest point. So let's move the point around and see if this is the highest. Oh, this one is the highest, 6.8. So you basically moved, make sure the point in front of it and the point behind it are all smaller than that. So that's the local maximum point. So the time difference is the period, right, between the two crests. And by the way, here, this is the period, not the wavelength, because this is a time graph. The horizontal axis is the time, so not distance. So be careful. This, I'm calculating period here. If you want to get the corresponding wavelength, then that's a more complicated calculation that we'll do in physics 11. So you can read the period here, 6.8 minus 5.05, which is 1.75 seconds. And you can get that from here as well, from the bottom. So between two cells, one of them here, it's 5 point, is this the maximum? No, 5 point, yeah, I think 5.95. Okay, so 5.95 seconds is the other, is the child, the first child, and the second child is I think 7.7. Yeah, 7.7 is the local maximum, and 7.7, and this one's the 5.95, right? 5.95, and the difference between them is also 1.75, right? So you can get the period from either the crest or the child. And if you look at the velocity graph, it's the same story. By the way, I will explain why velocity time graph is also a wave graph in a second. And you can see you can use those 2 points on the velocity time graph and get the same, you will get the same result. So for the velocity, actually, I have a screenshot of those graph. So to save some time, let me show you the screenshot here. All right. So those are the position time graph I just showed you, and those are the points I just labeled. And then you can see like this is 6.8, 5.05 minus 5.05 is 1.75 seconds. This is from the child, from the crest, and then from the child, which is 7.7, 5.95, and then you get the same answer, 7.7 minus 5.95, 1.75 seconds as well. Right, so the period is 1.75. And if you look at the VT graph, so between the two crests, it's 6.4 minus 4.65, which is 1.75 as well. Right, so it's actually the same period for PT and BT graph, and they are all wave motions. Okay. Let me explain why the VT graph is also a wave motion. So let me turn the camera. All right. So this is the velocity. Right now, it's at the equilibrium, right? But I'm gonna pull the cart, and then the spring will push on the cart, will pull on the cart, which will accelerate the cart up the slope. So the speed will increase until it reaches the equilibrium. And after that, the speed will decrease and to 0. Then from here, the compressed spring will push it down. So the speed will increase again until it passes the equilibrium. Then after that, it will decelerate until it gets to the end. Velocity becomes 0 again. And then the stretched spring will pull it back. So the speed increases again, and then it repeats. Right? So you can see the velocity is also from equilibrium and increase to a certain extent, then go back to equilibrium, and then go to the other direction, then keep repeating the pattern. Right? So that's why the velocity is also a wave graph, because it has this oscillating feature. The same with position. Position is pretty visual, right? Position is like you can see it going back and forth. But velocity, in terms of the speed, right? It also has that pattern. Speed 0, speed 0, and in the middle, speed is the highest. And this actually ties into the next thing I'm going to talk about. It's the relationship between the wave motion and the relationship between the wave graph of PT graph and the wave graph in the VT graph. Okay. So let me switch back. To my phone app. All right. So as I was saying, both the PT and VT graph are wave graphs, but they are not the exactly same pattern. In fact, they are different, but they have really interesting relationships that we call, the technical word is phase shift. So I'm going to put it in simple words. It's basically one of them, for example, one position, reach the equilibrium, and then the velocity actually will be at its highest point. And then after about a quarter of the period, the velocity will go back to the equilibrium and the position will go up to the maximum. So it's like like velocity is lagging the position or the other way around. So one of them is leading, one of them is lagging by a quarter of the period. Okay, I'll explain it in details. So if you look at this point on the PD graph, this point at the equilibrium point, and look at the time, 4.65 seconds. Okay. By the way, this is not exactly 0, but it's close enough. It's on the order of 10 to the power of -4, and you can tell from the graph it's essentially at the equilibrium position, P equal to 0. At that exact moment, 4.65 seconds, let's take a look at the VT graph. You will notice something really interesting. The highest point, 4.65 seconds, right? Keep that in mind. See, at 4.65 seconds, this is the highest velocity, right? Show you a point next to it, smaller. show you point to the left of it, smaller. So at 4.65, this is the local maximum velocity. Isn't that interesting? At 4.65 seconds, the position is 0 at equilibrium, but the velocity reach is maximum. Okay. I actually also have the screenshot of this, so I'm gonna show you that. So put them side by side, so you can have a better view. Okay. So here, as you can see, this is the equilibrium position of PT graph. So this is the PT graph at 4.65 seconds. And at that second, the VT graph, it reaches the local maximum. When P is 0, velocity is actually the highest. And in a quarter, this is a quarter of the period, about 0.4 seconds, you can see the speed then will go back to equilibrium. And during this same period, the position will actually go up to the highest. So they are like, one of them is lagging, one of them is leading. So they position become equilibrium, velocity highest, then position will become highest, velocity go back to equilibrium, then position go back to equilibrium, then velocity go to the negative maximum, then position go to the negative maximum, right? So the difference, this is what we call the phase difference or the phase shift. It's a quarter of the period. You can see from the graph. And why is that? So let me explain again with a smart card. Why is that? Sorry, I know I'm switching constantly between different things. All right. Hold on a second. All right. So actually, I already explained it a little bit just a few minutes ago. So basically, the idea is right now it's in the equilibrium position, right? So then I pull it and will initiate a wave like oscillating motion, right? So at this point, the position is high, the maximum, right? Because from the equilibrium, this is the highest position. But the speed is 0, right? Which is consistent with the graph. The speed is 0. And then if I release it, the stretched spring will pull on the cart, pull it back to the equilibrium. And during this process, the cart is being accelerated. Okay? But past, so that's why when position is 0 at the equilibrium position, the speed is the highest because it's being accelerated by the spring. And past the equilibrium position, the spring is compressed. So there's a force down the slope decelerating the cart. And then eventually the velocity becomes 0 when it has a negative maximum position, right? So you can see also from here why velocity and position are not exactly synchronized. They are a quarter period apart, right? So when in the middle, highest speed, but position 0. At the two end, position highest, but speed is 0. So there's a lag between the two. Okay. So I think that's it for this lab.